Okay, welcome in. We're in Module 6 right now, and this is on exponents and scientific notation. So let's dive into it. We are going to go through these objectives. We'll use the properties of exponents and convert from scientific notation and decimal notation, and then back. And then we'll perform computations using scientific notation and solve applied problems using scientific notation. So we'll start by talking about properties of the exponents. If I have two things multiplied by each other, b and b, but they have different powers. So this is b to the m and b to the n. They have to have that same base. That b has to be the same, or else this doesn't work. But if I do have that and they're raised to different powers and multiplied, then it's the same thing as having that b raised to the sum of m and n. So example over here, 9 raised to the 6 multiplied by 9 raised to the 12. I'll just add 6 and 12, and so that's 9 raised to the 18. We won't worry about what that equals. It's a very large number, right? The power rule, if I have b, some number, any number, raised to a power, and then that whole thing is raised to a power again, then those powers get multiplied. So for example, 3 raised to the 4, and then that whole thing raised to the 5th is the same as 3 raised to the 4 multiplied by 5, which is 3 then raised to the 20. Or 5 raised to the 3, and that whole thing raised to the 8 is 5 to the 24th, because that's 5 raised to the 3 times 8. Now our quotient rule, if these are divided instead of multiplied, b raised to the m, b raised to the n, and again, it's b, they both have to have b, whatever that number is. It has to be the same number raised to these powers, or else this doesn't work. Then I have b raised to the upper power, m, minus the lower power, n. So for example, 5 raised to the 12 divided by 5 raised to the 4th is 5 raised to the 12 minus 4, or 5 to the 8th power. Likewise, 9 raised to the 40th power over 9 to the 5th power is 9 to the 40 minus 5 power, which is then 9 to the 35th power. If b is any real number, then b raised to the 0 is 1, right? So for example, 3 raised to the 0 is 1. 4 raised to the 0 is 1. 250 raised to the 0 is 1. This works for anything that b could be except 0. 0 raised to the 0 is what we call undetermined. We don't play with it, right? We don't have 0 to 0. We don't like that. So it's just an undetermined value. We don't really know what that is or means at this point, right? Some examples of this, again, 7 raised to the 0 is 1. Pi is a number, is 3.1415. It goes on forever, but it's still a number. That raised to the 0 is 1. Be careful with your negatives, right? -5 inside of parentheses is raised to the 0. That is 1. But -5 to the 0 without those parentheses is the opposite of 5 to the 0, which is the opposite of 1. If the negative is not on the inside of the parentheses, be careful with those. It's not affected by the 0 power. And then likewise, if I have a negative exponent, b to the -m is 1 over b to the m. Right? So that is to say, excuse me, if I have 2 raised to the -3 power, I can take that and put it in the denominator with a positive exponent, and I get 1 over 2 to the 3 power. Some more examples of this. 8 to the -2, I can put that in the denominator with a power of +2. And then they've worked this out. They've taken 8, squared it, and you get that 64 in the denominator. Likewise, 5 to the -3 power, that all gets written down in the denominator with a 5 to the +3rd power. 7 to the -1 power gets written in the denominator as 7 to the 1st power. Powers of 10 are useful. We'll see that they're useful in a little bit. They're going to come into play with scientific notation quite a bit. But if I have, say, in this case, we've got 10 to the ninth power, that's 10 times 10 times 10 times 10 times 10 to 10 to 10 to 10 to 10. They're 9 tens, right? So if I multiply those out, you'll find that I have 1, 2, 3, 4, 5, 6, 7, 8, 9 tens, right? 10 to the third is going to be 1,000. It has 3 zeros. 10 to the fifth is a 1, 1, 2, 3, 4, 5 zeros. Right? So whatever that power is will tell you how many zeros there are. But if I have a negative exponent, right, it can go the other way. 10 to the negative 9 means my decimal was here for a moment if it's just a 1. But to the negative 9, I'm going to move that 9 spaces to the left. So 1, 2, 3, 4, 5, 6, 7, 8, 9. But that means I have 1, 2, 3, 4, 5, 6, 7, 8 zeros after the decimal, right? So if I have 10 to the negative 16, that's a 0 followed by 15 zeros and then my 1, right? 0 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and then the 1, right? So we must be careful of those negative exponents, right? But they're very easy as well. So scientific notation is a way of writing rather large numbers, right? For example, if I wanted to write the number 199, that's 0, 0, 0, 0, 0, 0, 0, right? If I came across this in a book and it were just written like this with no commas, I would just be like, oh, a really big number, an obnoxiously big number. If they do throw the commas in there, yoink. Then it's a little bit easier. I have the ones, the thousands, the millions, billions, trillions, quadrillions, and quintillions. So this is 1 quintillion and 990 quadrillion. Whatever we want to call this, it's obnoxiously large, right? So rather than writing this in this way with all those zeros, scientific notation comes and says, well, we're just going to rewrite it like this. And the idea here is to have just one digit in front of a decimal, and then anything else that's important after it, and then multiply it by a power of 10 and clean up all those zeros. So A, the number in front is supposed to be a number greater than or equal to 1, but less than 10. So A should be somewhere between 1 and 9.9999 something, right? But we should always have just that very first decimal. So I'm going to take my decimal that is normally right here. I'm going to take it all the way and put it just to the right of my very first non-zero number. So I'll write this as 1.99. I'm going to ditch all of these zeros that I don't want to write and then just write times 10 to whichever power is necessary to take this 0 from where I've now put it. I don't know why that keeps happening, and go all the way back, right? So I would have to move it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 places to the right to get my original number back. And so this is that same number in scientific notation. Now, this is, let me see if I have an eraser here. I do. It's not a grader. There we go. Now, this is also very useful for very small numbers. And I don't mean very small numbers like 1. I mean very small numbers like the size of an atom. If I have a very small number like 0.0000000, I mean, do you get where I'm going with this? It's obnoxiously small. 2, 3. First off, as we write these numbers, these decimal numbers to the right of the decimal point, we don't use commas. And so we can't make life easier on ourselves by throwing commas in. So it's just horrific to read a number like this. So what I'm going to do is the same thing. I'm going to take this 0 and I'm going to move it all the way to the right. And this is true in both cases, to the right of the first non-zero digit. So all right, this is 2.3. But now I've got to go times 10 to the whatever number is going to make my new number here, this 2.3, whatever number, whatever power of 10 is necessary to push that decimal back to the left, the appropriate number of spaces. How many spaces do I have to move it? Well, to get my original number back, if my decimal is now between my 2 and my 3, that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 to the left, because it's a movement to the left that I need to make. That is a negative 12, meaning move this thing 12 spaces to the left and you get your number back. And this is that small number in scientific notation. So let's take a look here, write each number in decimal notation. We can go back and forth between these two. 1.375 times 10 to the 10. This is telling you how many to move. It's positive, so it's a movement to the right. So I'm going to take my 1.375 and I'm going to move it to the right by 10 spaces. Now, if there aren't 10 spaces, I'm just going to zero fill. So I'll just graphically put these little loops here, these little dips. So 1 space, 2, 3, 4, 5, 6, 7, 8, 9, 10, and I'll throw my decimal right there, maybe. And then zero fill this. And then it's fairly messy here, so I'll rewrite it as 1, 3, 7, 5, and then I have 1, 2, 3, 4, 5, 6, 7 zeros. 2, 3, 4, 5, 6, 7, and I'll throw in my commas to make it look somewhat decent, right? So that's 13,750,000,000, right? Likewise, with this number here, I'm going to rewrite it as 1.1, but this times 10 to the negative 4 is telling me I need to move this thing to the left by 4. So this decimal goes to the left 1, 2, 3, 4. Again, I'm going to just zero fill any spaces that weren't there. And if I have a decimal that is the beginning of my number, I'm going to start this with a 0. So I'll write this as 0 point, and that's just kind of common notation for decimals to throw the 0 in front. 0.00011, and that is that number as a decimal. Excuse me. So let's take a look at, oh, well, that's helpful. I will erase that. If you'd like to read it through this, I can't erase. There we go. If you'd like to read through that, go ahead and pause it now, not now, and now read through it, but it's essentially what I've said. And they work it out. All right. To go the other way, we've kind of done this already. We're going to take that decimal, and if there's not one already, I'll place it at the end of the number. So 4,600,000. I'm going to put the decimal right here. If it's not there, I'm just going to plop it there. All right. And then I want to write this in scientific notation. So this guy has to come all the way over to the right of my first non-zero digit. So I'm going to write 4.6, and then all of these other zeros I dump in the trash. I don't need them. They're gone, right? But I do need to consider their spacing. So 4.6, and then I'm going to erase this because I have a habit of making things so much messier than I think is really necessary. But the number of spaces that I would have to move from where I've now placed my decimal, which is right here between the 4 and the 6, that is a movement to the right of 1, 2, 3, 4, 5, 6. So the power of my 10 is 6. So in scientific notation, 4.6 times 10 to the 6. Likewise, with this decimal on B, I'm going to take it all the way to the right of the 2. So I'll rewrite this as 2.3, omitting all of those leading zeros, and multiply this by 10 to the power of how many spaces I would have to move the decimal from where I've put it to get it back to where it was. 1, 2, 3, 4, 5 to the left, or 5 in the negative direction if you like. But that is a negative 5 power. Oh, and they work these out as well. All right. Now, if we are multiplying, so we have some operations that we may have in scientific notation. So I'm going to just jump straight into it. If I have these two numbers, 3.4 times 10 to the 9 times 2 times 10 to the negative fifth, what I essentially have is, in scientific notation, I have two things multiplied. And if I multiply those by another number in scientific notation, I have A times B times C times D. I don't really need these parentheses. I can rewrite this as A times B times C times D. And multiplication is commutative, which means you can do it in whichever order you feel like doing it in. So if I want to do a restructure here, I can rewrite this as A times C times B times D. And all I've done is switched around B and C here. But this is valid because it's just a string of multiplication. And because it's just a string of multiplication, I'm gonna write this out here. We'll look at this 3.4 times 10 to the 9. I'm going to get rid of the parentheses and just put my implied multiplication between the 10 to the 9 and the 2 and times 10 to the negative fifth. And I'm going to swap the position of these two. So I'll rewrite this as 3.4 multiplied by 2 multiplied by 10 to the 9 multiplied by 10 to the negative fifth. Now again, this is multiplication, so it's just all multiplication. I can do it in whichever order I want to. I can take these two and multiply them together. And this is a case where I have b to the m multiplied by b to the n, one of the first things that we talked about. So if I have b to the m times b to the n, that is b to the m plus n, which is to say, in this case, I have 10 to the 9 multiplied by 10 to the negative fifth. This will result in 10 to the 9 plus negative 5, or 9 minus 5. So this is 10 to the 4. Oops, that is this portion here. Now, in a separate multiplication, I'll take 3.4 and multiply it by 2. That just gives me 6.8, right? So now up to this point, I have 6.8, and I still have that being multiplied by the second part. So that is 6.8 times 10 to the 4. And wouldn't you know it, that is a number in scientific notation, and that is the result of 3.4 times 10 to the 9 multiplied by 2 times 10 to the negative fifth. Now, it's not always that easy. We might run into, let me see if they have an example here. I'm going to just back up right here, get some clean screen here. Hey, I can do that all at once. That's nice. Let's take a look at a number such as 7.2 times 10 to the fifth. And then we're going to multiply that by, let's say, 3.4 times 10 to the 7. Right? Now, I will cheat a little bit. I won't show all of my work with 7.2 times 3 to the 4, but I will show that we can do that same kind of trick. I don't need the parentheses, and I can rewrite my multiplication. So I'll write this as 7.2 multiplied by 3.4, and I'll work that out, and then I'll work out 10 to the 5th multiplied by 10 to the 7th. Like we had done before, 10 to the 5th times 10 to the 7 is going to equal 10 to the 5 plus 7 power, or 10 to the 12. And then 3.4 times 7.2, again, I'll just cheat. I'm going to throw this into a calculator, because the point of it is not, you know, the longhand working this out. This ends up being 24.48. So in the end, my answer is 24.48 times 10 to the 12, but this is not in standard scientific notation anymore, because my number in front of my decimal is 24. I should only have one number in front of the decimal, right? So I have to compensate here. I have to fix it. So I'm going to take that decimal and I'm going to move it one more spot to the left to get it to where I need it to be. So it's 2.448. And I can think of this as I started with 24.48 and I made this smaller by turning it into 2.448. So to compensate for that, my power of 10 to the 12 has to compensate by getting bigger. So I moved it one decimal place. I'm going to increase my power 1. So that becomes times 10 to the 13. So it's not, I mean, it's hard to say that that's not frequent. You won't run into that, but you probably will. So it is something you want to be aware of, right? Now, the next thing that we would talk about is fractions, right? Once again, if I have two things being divided, I can treat those times 10 to the n and times 10 to the m's as exponents in two things being divided. So let's take a look at, well, there's one completely worked out. So I guess I won't be doing this one bit by bit, but I'll explain what they've done. We have 8.4 times 10 to the negative 7, and that's being divided by 4 times 10 to the negative 4. So I'll treat this as 8.4. Oh, they've already done this. So I'm just going to separate it. 8.4 divided by 4, and then I'll treat the 10 to the negative 7 over 10 to the negative 4. So the powers become 10 to the negative 7 minus negative 4, which they've written here. Negative 7 minus negative 4 is the same as negative 7 plus 4. That is negative 3. So I have negative 3. And then in the division, 8.4 divided by 4, that's 2.1. So I end up with that 2.1 times 10 to the negative 3. And if you want to write it in decimal notation, you can, of course, do that by moving it to the left by 3. So let's look, oh, they have the solution here as well. We're looking here, as of April 2021, in this example, the national debt was $28.1 trillion, or 28.1 times 10 to the 12 dollars. At that time, the US population was approximately 331 million, or 3.31 times 10 to the 8. If the national debt was evenly divided among every individual in the United States, how much would each citizen have to pay? So we would take that debt divided by the number of people, right? And they've worked it out here. The total debt, 28.1 trillion divided by the number of people here. Again, you separate those numbers. Why? Let's time out. All right. I have just the slightest issue. This is not scientific notation. It's not wrong. It's still 28.1 trillion, right? But that's okay. The point here isn't, I suppose, to be exactly in scientific notation, but it is important to note that the way they've written this, 28.1 times 10 to the 12, is not scientific notation. It's not going to stop them from doing the problem, though. It is going to stop them from one thing that I'm going to talk about, which they apparently purposefully wanted to avoid. But here we go. I'll do the division. 28.1 over 3.3 gives us 8.49-ish. They've rounded that number. But then they take this 10 to the 12 over 10 to the 8 as 10 to the 12 minus 8, which is 4. And so we have 8.49 times 10 to the 4, meaning every person in the US, if we ponied up about $85,000, then we could be back at zero. Now, the thing that they tried to avoid here is if I have the scientific notation number of, let's say, 2.3 times 10 to the, I don't know, fifth, and I want to divide that by 6.1 times 10 to the, let's go 2. Then I can treat this as 2.3 divided by 6.1, and then my 10 to the fifth over 10 to the 2. So in the end, this portion of it ends up being 10 to the 5 minus 2, or 10 to the 3. The other portion of it, this 2.3 divided by 6.1, is about, I'm going to round this because it goes on forever. So this is about 0.377. So in the end, the number that I have is, and I'll write it up here because I'm going to clear my screen, 0.377 times 10 to the third, which is again not in scientific notation. Because it starts with a 0, right? In order to get it into scientific notation, I have to do a couple of things. Let me clear up some space here. If you needed that work, rewind it 5 seconds and pause it. But I need the space, so it's gone. So now again, I'm not in scientific notation. I want to be, right? If your answer is, you have to write your answer in scientific notation sometimes. If that's the case, we need to convert it. So again, I'm going to take that decimal and I'm going to move it over that, wrong direction. I'm going to move it over, not that way. So it's to the right of my first non-zero digit. So I'm going to write this as 3.77. And then this times 10 to the, but again, I went from 0.377 to 3.77. So I made this bigger. And so I have to make my power of 10 smaller. And I made it bigger by 1 move. So I have to make my power of 10 smaller by 1. And so this is times 10 to the 2. The other option is to completely convert this into a decimal and then back into scientific notation. But this is kind of just a quicker shortcut between the two so that you don't have to take an intermediate step of turning it back into a decimal number. Anyway, that is it. And if you had any questions, feel free to reach out to me. But thanks for being here.